Welcome to today's Explainer, where we're basically attempting the ultimate scientific heist. We're going to try and crack the universe's greatest code. We're diving into a complete, mind-bending paradigm shift that actually promises to solve the absolute preeminent challenge in modern theoretical physics. And you know what that is, right? Uniting general relativity with quantum mechanics.
So what do a Webby-winning AI researcher, a string theorist, and black holes all have in common? Well, to figure that out, we're bringing together three entirely different scientific breakthroughs to propose a truly revolutionary unified theory. And the theory is this: space-time itself is actually a neural network. Now, I know that sounds like straight-up science fiction, right? But by the end of this explainer, you'll see exactly how the literal mechanics of artificial intelligence might just be the very engine of reality.
Let's kick things off with Section 1, the quantum gravity paradox, and look at general relativity versus quantum mechanics.
Okay, so we've got these two incredibly successful theories that absolutely refuse to work together. On one side, we have Einstein's general relativity dictating the macroscopic dynamics of space-time. It conceptualizes gravity as this beautifully smooth, continuous geometric manifold, kind of like a perfectly smooth sheet of silk. But then, on the exact opposite side, we have quantum mechanics, governing the microscopic realm. And that is just full of discrete, chaotic, probabilistic, and heavily entangled states, literally like a chaotic boiling pot of water. So it is notoriously, stubbornly difficult to reconcile this smooth cosmos with those chaotic quantum microstates.
The core challenge here is just conceptualizing how continuous geometry can possibly emerge from discrete, jagged little blocks. If you look at the framework of causal dynamical triangulations, we see the literal atoms of geometry that theorists use to piece together a quantum spacetime. But here's the billion-dollar question. How do you zoom out from these chaotic, jagged little triangles to get the beautifully smooth, predictable universe that we actually see and experience?
To really highlight just how difficult these dynamics are, just think about the sheer weakness of gravity compared to other forces. Think about this for a second. A tiny, cheap refrigerator magnet holding up a paperclip easily overpowers the gravitational pull of the entire Earth. The math involved here is just incredibly sensitive. As Demesis Hassabis, the head of Google DeepMind, pointed out, it's really hard for us humans to make any kind of clean predictions about highly nonlinear, dynamical systems. We basically need an entirely new mathematical language.
Which brings us to Pillar 1, Juan Maldacena and the holographic principle.
Back in 1997, Juan Maldacena completely shook the physics world when he proposed the ADS/CFT correspondence. He mathematically proved that a three-dimensional string-theoretic bulk space, specifically what we call an anti-de Sitter space, is literally indistinguishable from a two-dimensional conformal field theory that exists purely on its boundary. Think of it like a flat two-dimensional surface perfectly projecting a three-dimensional reality. It's a full mathematical duality. They are essentially just different languages describing the exact same physics. So the absolutely crucial takeaway here is that gravity isn't fundamental at all. Instead, it's an emergent, holographic manifestation of lower-dimensional quantum entanglement. The outer boundary holds all the quantum information, and as you move inward into the bulk space, that extra dimension basically acts as an energy scale. We even have the Ryu-Takayanagi formula, which proved that entanglement on the boundary is strictly proportional to the geometry inside the bulk. Simply put, space-time is literally built out of quantum information. Now, let's pivot sharply for Pillar 2, Geoffrey Hinton and deep representation learning.
In statistical physics, there's a really important concept called renormalization group flow. It's basically how physicists coarse-grain, chaotic microscopic fluctuations to find smooth, large-scale physical laws. Well, it turns out that is exactly what deep neural networks do. Geoffrey Hinton's incredible work on knowledge distillation demonstrates exactly how networks compress structural information across different scales. You input high-resolution, wildly complex data, like, say, a chaotic quantum boundary, and as that data flows through the hidden layers, the network algorithmically extracts the latent features and just completely discards the noise.
And this is where things get wild. There is a literal mathematical dictionary proving the ADS/DL isomorphism. It shows that bulk spacetime operates functionally as a deep neural network. Look at how they line up. The boundary quantum field is the input layer. The bulk geometry? Those are your hidden layers. The flow deeper into the space maps to the depth of the network. And the metric of spacetime itself? Those are literally the trained weights of the neural network. So solving Einstein's field equations is mathematically equivalent to training this network to minimize its loss against the boundary data.
Mind-blowing, right?
Moving right along to Pillar 3, Prakhar, Kaushik, and universal subspaces. But right about here, we hit a massive roadblock. If space-time is a neural network with billions of fluctuating parameters, why isn't our universe just a chaotic, unstable mess? Why don't we all just fall apart instantly?
Enter AI researcher Prakhar Kaushik. To resolve this exact paradox, he analyzed over 1,000 massive deep learning models across totally different modalities. We're talking language models, vision transformers, you name it, he looked at it. And he discovered something incredible called the universal weight subspace hypothesis. He found that overparameterized networks just don't stay chaotic. Instead, they predictably collapse into stable, highly restricted, low-dimensional manifolds, completely regardless of their tasks or how they're initialized. Out of billions of parameters, almost all the variance is captured by just 16 to 32 principal components. The network naturally, inherently discards the high-frequency chaos.
This brings us to our final section, the grand synthesis, the holographic neural universe. So let's smash all three of these pillars together. The smooth metric of space-time that we experience every single day is simply the result of the universe's neural network collapsing into a shared spectral subspace. Those wildly fluctuating quantum microstates, they're just unconstrained neural states. But as the universe processes this information, it deliberately discards the chaotic quantum noise, leaving behind the beautifully smooth, stable manifold of classical space-time. Which means gravity isn't even a fundamental force. It is quite literally the thermodynamic byproduct of the universe minimizing its loss function.
Now, this framework completely redefines the physics of black holes. The famous Bekenstein-Hawking equation shows us that the entropy, or the information, of a black hole is actually strictly proportional to its surface area, not its volume. When you view this in the context of deep learning, black holes are essentially the universe's ultimate autoencoder bottleneck layers. Think about it. An autoencoder forces high-dimensional input into a tiny, compressed, latent code before rebuilding it, right? Well, the black hole event horizon acts as the exact physical analog of a neural bottleneck. It physically forces the massive informational complexity of the quantum boundary into a minimal surface area.
By aggressively filtering out high-frequency quantum errors, essentially acting like a giant cosmic error correction code, the universe extracts order from chaos. The smooth geometry of reality is reconstructed from a low-rank projection of data, and that ensures our macroscopic reality remains firmly intact and stable, exactly as we see mapped out in lattice quantum gravity models. All of this leaves us with a truly profound, lingering question. If the universe operates as a holographic neural network, constantly collapsing into universal subspaces and optimizing its thermodynamic loss function, what exactly is it trying to learn? Are the fine-tuned constants and symmetries of our physical reality simply the inevitable mathematical attractors of a cosmic algorithm? It's an absolutely stunning new lens through which to view reality, and honestly, one that just might be the key to the ultimate theory of everything.